Hello CE8 students and welcome to Lab 3. Lab 3 this week is discussing differential leveling. So first let's discuss what is the purpose of differential leveling and what does it do for us? Well, in general, differential leveling is used to establish new temporary benchmarks for construction sites and other projects or improvements being done. Most commonly probably civil structures and stuff. However, this can be used for building new buildings or new bridges, roadways, pretty much anything that's going to require a construction site and surveying, you're going to use differential leveling for. So, what this is typically done with, like I said, we make temporary benchmarks. However, to do that, you typically need some sort of starting point. A starting point with known statistics, known elevation, or a known GPS coordinates. And so throughout the US, there are numerous benchmarks everywhere. Many of them put out by the US Geological Survey, but other entities also put them out as well. And actually the one we'll be talking about here in a minute is by VTA. However, in general, they're placed in lots of different places in order to enable people who need to survey to access something that's a set location with set statistics that we can then use in our projects. So, for example, in this, if this is the engineering building that we would typically be in if we were in person, and this is San Fernando Street. Okay, if we walked out to the north side of the building and went down San Fernando, right about here on the curb, you would find in the curb this little metal dial. And that metal dial we're going to call benchmark 1. And you can call it, in general, VTA 216, because it's the VTA survey marker 216. Okay, and I've got that listed here in our table. So be sure to reference this table when you're doing your own table in your own field book as to how to create a table and what it should look like. You can also check the Excel spreadsheets that I'll post on Canvas. So, we have a known benchmark that was preset for us, and we know the elevation of this is 86.16 feet above sea level. Okay. Using this information, what we will be doing is we will, in essence, be making a new temporary benchmark over here near Tower Hall. If we were doing in-person classes, the majority of our labs would be done around Tower Hall because it's a wide open space around most of Tower Hall, so we can easily work there without interrupting a lot of people in the grassy areas. It also enables all the teams to be able to easily work around each other using equipment that has to be used over, possibly hundreds of feet. Okay. So you might go, well, why do we need a temporary benchmark if we already have one here? Okay, and the reason for that is that, first one, it saves time. If I don't have to come all the way from the original benchmark out to Tower Hall to establish elevations, that just saves me time if I know I can start right beside it or somewhere much closer. Secondly, the more times you have to do something, the more opportunities you give yourself to create errors. If we can do this one time very accurately, verify our accuracy, then we know moving forward that whenever we start projects at that point near Tower Hall, we're starting at an accurate elevation and can work from there. Okay. So those are the two main reasons why we like to establish temporary benchmarks for easy reference. So, how would we do it? We complete what's called a differential leveling circuit. The circuit, as we already stated, starts at benchmark 1, okay? And it would require use of an auto level and a Philly rod, much like we saw in the video last week with the equipment that I posted. You'd use the same equipment. So what would happen is you have one group member who would go over to this benchmark and they would put the Philly rod directly on the benchmark, not a foot in either direction, but directly on the benchmark. And then let's say we're trying to get to the corner of Tower Hall and establish that as our new temporary benchmark. Well, we can't just go straight there. There's buildings and such in the way. So we're going to get there by going around buildings and using what's called turning points to get ourselves from benchmark 1 to our future benchmark. So first, as I said, one person would hold the Philly rod there on benchmark 1. The rest of the team would set up the tripod some distance away. It depends on the equipment. We typically in lab try to tell you to use around 100-foot distance, okay? So whoever's using the tripod would then backside in to benchmark 1. No, we're going to be making a circuit and working our way around. So if you go backwards in the circuit, it's a back sight. If you look forward, it's a foresight. So this is the back sight. And I am simply, for the sake of ease, I'm going to use some data that was collected a few semesters ago when I was in the class. Okay. And we're going to say that when we do this back sight, we get a height of 5.25 feet on our Philly rod. Okay. Once we have this height, we can then move the Philly rod off of benchmark 1, and we're going to move to what we call a turning point. And we'll put it right here, and we'll label that TP1. Okay. It's forward in the circuit. We're moving on, so we're going to take a foresight onto the turning point. And we're going to say that this one comes out to 3.57 feet. Okay? So, using this information, we can establish two things. We can establish the height of the lens of the auto level, so the part we actually look through. We can establish that elevation above sea level. We call that height of instrument. And then using that and the foresight, we can establish the elevation at this turning point. And we're going to continue to use that idea to establish the elevations moving forward, including our new benchmark. So, in this first turning point distance, we went from benchmark 1 of 86.16. We know, if you hopefully learned in lecture so far, that if you take an elevation starting, I'll use S for start, and you add the backside height, that will give you the height of your instrument. Okay? So here, 86.16 plus 5.25 comes out to 91.41 feet. So the height of my auto level is 91.41 feet above sea level. We take that, HI, we subtract the foresight, and that gives us our elevation new. And I'll put N for new. Okay? So, if we subtract those out, we get 87.84 feet. So that means, quite literally, that the elevation on the ground at the exact point the Philly rod is standing at turning point 1 is 87.84 feet. And we'll go ahead and label this TP1, so we know that that's what that is. Okay? So, obviously now that I do benchmark, so we're going to repeat this again. Whoever's holding the Philly rod stays there. Our equipment person leapfrogs them, sets up ahead of them. Once again, you back sight in. Okay, and our next back sight is going to be 4.17 feet. Okay, which gives us 92.01 height of instrument. They stay in place. The Philly rod person moves up further. Okay. This instrument cannot move. Remember, whenever we're leapfrogging instruments, the middle instrument getting leapfrogged cannot move. Moving that would possibly introduce errors, and we don't want that. So only one piece of equipment moves at a time. We foresight into this. We'll call this TP2. Okay. And we're going to say that this one comes out to 5.57. And when we subtract there, we get 86.44 feet. So once again, elevation of turning point 2 is 86.44 feet. Now, I'm just gonna, for the sake of simplicity, we're gonna pretend that this building is actually like this. So we don't have to do another trip to our benchmark, okay? Once we have this turning point 2 established, we once again move our equipment over here. We backside in. I've got a 5.05, I mean. That should be TP2. Okay. We know that when we put it in here, we're going to get 91.49. Then the Philly rod gets moved to the new benchmark. I want to note that whenever you're establishing a new temporary benchmark, much like the permanent benchmarks, this needs to be something that's not going to move. It's also got to be something that's going to be steady and stable. Okay? For example, if I walked and wanted to use the corner of Tower Hall and could easily mark where I put my Philly rod, that would work. However, we need to consider some things. One, is this covered in concrete? If so, that's fine, because I know that that concrete's probably not going to shift in elevation. Is it grass? Now we have an issue. Grass grows. It can change. It gets cut. It's in dirt. Dirt is soft. You can push it in. It can get expanded. So we shouldn't use anything that can change easily, such as grass, dirt, especially loose soil, flower beds, mulch, stuff like that. We should definitely find something that's steady, hard, and it's always going to keep its elevation. For example, the original VTA 216 is built into a concrete curb. That's probably not going to move for a long time. Same idea for temporary benchmarks. Once we find a spot that seems reasonable that we can consistently get back to, we'll put the Philly rod there, and we'll foresight into that. And we'll say that this one is 3.42 feet, which gives us a final elevation here of 88.07 feet. Okay, and we said this is going to be our new temp benchmark, so we're going to call it benchmark 2. Since you've already got a benchmark 1, and I'll label that here, benchmark 2. So now we know we have a benchmark 2 set, hopefully in a place that is stable and not going to change, and we know its elevation is 88.07 feet. So we have a new temporary benchmark. But not so fast. What if something has happened during one of these turning points that introduces some level of error? Now, it could be minute, small, it could be insignificant, or it could be massive. Let's say somebody moving from turning point 1 to turning point 2 sets up their tripod, and in trying to move around their tripod, they accidentally kick one of the legs of the tripod, and they don't notice. If you don't notice that, when you get to benchmark 2, you might just assume that this is an accurate measurement and we're good. But what we really need to do is we need a way to verify that this is still accurate and we haven't made any egregious errors along the way. So we do what's called closing the circuit. Closing the circuit means you have to bring your differential leveling circuit back to a known value. Okay? This could be a separate benchmark. If you're doing something like building a highway through a long stretch of farmland in the Central Valley, you would probably use one benchmark at one spot, and then you might possibly use another benchmark somewhere else. Here on campus, though, we don't have that luxury. So the closest one is still going to be this benchmark, and that's okay. Since we know what it is, we can go back to that and verify our heights. So what would happen is you would do the same things again from that point, and you would basically close the loop. So you would backside in, you foresight into a new turning point, you backside in again, then you foresight into that benchmark. Now here are only shown, I believe, 3 turning points and 2 benchmarks. This could take as many as it takes. If your closest benchmark is out in the middle of nowhere and you're like 1.5 miles away, you're going to have a lot of turning points getting to your new temporary benchmark. In our case, we're lucky it might not take so many. I believe when we did this, one of our circuits took 9 points, and this circuit took, I think, also 9. Okay. So, we close the circuit. How do we verify that our results are accurate? Well, at some point, you're going to have, turning point, possibly other temporary benchmarks if you want to establish more. But at some point, it's got to come back to benchmark 1 again. And hopefully, if everything was done perfectly, we're going to end up with 86.16 feet as our final elevation, because that's what it is. More than likely, it will be a little off. And that's okay within reason. typically we're looking for errors of less than 0.1 feet when we're doing stuff for our in-class labs. Now, depending on what kind of things you're building or what your project is, that level of error could go up or it could go down. So it just depends on what's being built. Okay, but typically this needs to be relatively close compared to what you're building. So, for example, in this last circuit, my team was able to get within 0.02 feet. We were off by very, very little, which is well within the mark. So we were fine on this time. However, on a previous circuit, we actually came out to, I believe, 86.48, which is obviously more than 0.1 feet off. It's 0.3. It's triple the size of our error limit. So all of the data from that first circuit, it might be somewhat close, but it's not very reliable, especially compared to our newer circuit, which is much more reliable, and more than likely we would use that data in our analysis because that data looks to be better. Okay, so keep that in mind. Also, as one check, this comes out nice. Okay, that's good. But now let's also check, not only could we have possibly made errors in messing with the equipment, but it's also totally feasible that we made a simple math error along the way. Here it's just addition and subtraction, but I've never met anybody who hasn't messed up simple addition and subtraction before. So what we would do is on every individual page that has data, you would do what's called a page check. And the page check is a very simple math problem. What we want to do is we want to make sure that all of our addition and subtraction was correct, so that our elevations make sense. So what we're going to do is we're going to compare two numbers, and those two numbers are the absolute value of sum of the back sites, which is all of these guys, all the way down, minus the sum of all of our foresights, which is this column. We add all those up and subtract them, we take the absolute value, and we get some number. That number should be equal to our starting elevation minus our final elevation, take the absolute value. If you've done all your math right, these should add up to the same number. Even if our final and front elevations are way off, this should still work out. And then if this works out, you know that if this doesn't work out well, that we made some error in how we took our data. If this comes out wrong, then that means you've done something wrong in your data analysis. And hopefully that means that this is way far off and will hopefully make it closer. But remember, this needs to be done on every single page, not just the final, not just when you're done adding everything. So in essence, I would do a page check here, and whatever my final elevation values are would start the next page. And then from there, I move on, and I so on and so forth, keep checking new pages. Okay? So, differential leveling is used in the establishment of new benchmarks, typically temporary. And doing so, since it always involves equipment and humans, has chances for error. So we need to find ways to mitigate that. One way is by closing the loop and always coming back to a known value. And the second is to perform page checks to make sure that our math is sound and we're not making any simple errors along the way. And that's it for Lab 3 Differential Leveling. I want to remind you that if you have any questions, feel free to either email me, send me a Canvas message, come to my open office hours on Tuesdays, or feel free to try to set up a time one-on-one with me if you need some extra help with something, or just have general questions. I'm always willing to spend some time with you guys to help you understand this, especially since I don't get that one-on-one time and in-class time to help people who need it. Otherwise, good luck with Lab 3.